In this video, we'll be describing a simple magnifier, which in other words is just a magnifying glass. This thing. Now, the object itself is very simple, and the way in which it makes images is also some way that we have already described. This is simply just a converging lens. And what we're doing is we're using the converging lens to make a larger virtual image. Since we've already gone through the ray tracings, we won't go too much into how the details of showing that it makes a larger converging images. That's from chapter 23. I'll kind of give you a applet to show you how it works, just again to make sure you can visualize what's going on here. But then we're going to spend most of our time talking about not how it's built, but instead talking about how to describe the magnification of it. Okay, so this is a converging lens. And I can, for example, show you the principal rays. Here are the three principal rays. The two X's are the focal points. And this over here on the right is the image that you see. If I am looking at, say, this pencil through a magnifying glass, my face is going to be over here. I don't want to see the pencil upside down. I want to see it right side up and larger, which means I have to move it in to here. If it is within this distance here with the X, I have a virtual image. That distance is the focal length. So physically what's happening is I look from the right. The pencil is the actual shape of this, the object, but what I see is that, the image. And depending on where I hold it, I see a larger versus a smaller version of it. If I'm very, very close, they're about the same size. And if I'm near the focal point, it gets enormously large. Also note that it gets further away. Looking at this virtual image is essentially what the purpose of the simple magnifier is to create this larger virtual image. And that's what you're seeing here, is this is the larger virtual image as you look through a simple magnifier. Now, that was the simple part. Basically, this is a single lens. You'll have one in lab, you'll take a look at it, you'll see you can magnify things. The function is not hard. What is tricky to understand is how to describe the magnification. So here's why. What the magnification we've talked about so far is physically how many times larger is the object than the image. Okay? So if this arrow is the object, it'd be the height of this arrow, and this is the image, that'd be height of here. So if I'm looking at this, it's literally how many times larger is this image than that. Now, here's the tricky part. That is not, if I looked at the screen and I put a ruler up to the screen and say I had this stamp and then another stamp that was, not, I can see it directly in the same location. It's not literally how many times larger it is on the screen. Okay? So for example, this stamp right here is maybe half the height of this one, maybe a third by eye. That does not mean that the magnification we've talked about is 3. Okay? Why not? That would assume that this image I'm looking at is at the same location of that. For example, if this was actually very, very close to my face, and that was far away from my face, this could actually be a smaller object than that. It would just take up more of my view because it was closer. Or, equivalently, this could actually be the size of Mount Everest if it was sufficiently far away, like miles away. So I can't necessarily tell how tall this stamp is, how many inches tall it is. All I can really see very easily from this picture is how much of my field of view it takes up, which is the same thing as how much of the picture does it take up. And that is fairly straightforward. That's about 2 or 3 times larger than these other stamps. But to say that it takes up 2 or 3 times the amount of my vision, of my field of view, is to give you the angular magnification, not what is the magnification we talked about before, which is the lateral magnification. I'll introduce that term, lateral magnification, just to mean now we have a new magnification. I want to make sure if I say magnification, I'm going to be very clear about which of these two I'm going to talk about. So the old magnification is lateral, the new one is angular. If I just say magnification, it depends on context, whether I mean angular or if I mean lateral. So whereas the lateral magnification is the ratio of their heights, the literal size of the object in the image, this is the ratio of the angles that I see from my point of view. So, for example, if my eye is right here, I see the image as being this large, that angle, from the center to the tip. Okay, so that could be, for example, as I look at this stamp with my eye, how many degrees are there between a ray that goes from my eye to the top of the stamp and a ray that goes from my eye to the bottom of the stamp. Okay? The object can have a similar angle. I could talk about how many degrees is it from a ray that goes from my eye to the top of this stamp to compared, and the other ray would be the one that goes from my eye to the bottom of that stamp. What's the angle between that? And if I do the ratio of those angles, that would give me the magnification. And I'm using this stamp randomly just because I don't have a version of looking at the physical stamp itself. So I'm referencing this as if it was the actual object, even though physically it's not. But I would expect the stamps to be all around the same size and around the same distance. Now we denote the angular size of the object as having a little 0 at the beginning. So that's just standard terminology for original, essentially, gives you a little 0. And the width of the lens is without, it doesn't have the 0, it just says theta. Now, that's the basic idea of angular magnification. It's much more closely related to what you actually see with your eye. Okay, and it's much more useful also. If you want to say, can I use this thing to see fine details on some object, like this stamp, which is really what you use magnifying glasses for, the angular magnification tells you a lot more than the lateral magnification. And here's why. Imagine I had this fictitious lens. And this fictitious lens is going to take an image of a mountain. Huge object, but it's very far in the distance. Okay? And somehow, this fictitious lens made an image that was 3 feet high. Okay? So like the size of a poster. And I projected it onto a screen, for example. And I could walk up to it just like I could a poster. Now, if I was standing right up by that image, it takes up most of my field of view. Just like if I stood up right beside a poster, it would take up most of my point of view. And I could see the little crags and the little nooks and crannies of the mountain pretty well. Whereas if I turned and looked at the mountain that was maybe, say, 5 miles away, it would look like a little teeny speck on the horizon, and I couldn't make out the nooks and crannies of it. So the version that is only 3 feet high, but right in front of me, is very, very useful for being able to see the fine details. But the version that is very, very large, but very, very, very far from me, the actual mountain, is not very useful for seeing the fine details. And the thing is that the actual lateral magnification would be a number that's almost near 0, which is to say that the image is only 3 feet tall, but the actual mountain is like 1,000 feet tall, or thousands of feet tall. So that means that the magnification, which is the ratio of those two heights, is almost 0. It shrank it down so small that it was virtually disappeared. Essentially is what the lateral magnification would say. That's true. That if I walked up to the mountain and I was a foot away from the mountain and it was ginormously large, I could see far finer details than if I was up to the within a foot of the 3-foot image of the mountain, where I wouldn't be able to see it so clearly. But the distance away matters for how well you can see fine details. If it is very far away, it doesn't matter that it's much bigger because those details are so teeny in my field of view. And so what you'll often get if you look at just the lateral magnification, is absurd things like an image you can see much better has a magnification of 0, even though to your eye it'll look enormously larger. It'll take up a much larger field of view, most of your vision, as opposed to a little teeny thing on the horizon, for example. Or in the other way, that it might look like it's enormously large magnification, but it actually is harder to see the fine detail in it. So it's not a very useful tool to use this lateral magnification to tell, can I use this object in order to see my image very clearly. And the angular magnification is a much better gauge of whether or not you can see crisp objects, you see fine details in that image with your eye. Okay? So what we're going to do is think about, how do I describe the magnification, an angular magnification for this lens? Now here's the difficulty you're going to face with angular magnification. Angular magnification depends on where you, the viewer, are. If you have the lens in exactly the same spot, you have the object at exactly the same spot, so the image is exactly the same spot, but you move around, you'll see different angular magnifications. So here's a picture that's trying to illustrate that. If you view far from the lens, the image will have a larger angular magnification. In this case, it will be larger than 1. The image will take up a larger field fraction of your view than the object would. But if you moved your face right up against the lens, they would take up the same amount of your view. And so the angular magnification would be 1. So if I listed an angular magnification for a lens, which is what they say, like a magnification of blank for a lens, that's what they mean, it's assuming that my eye is placed in a particular location in order to list that number, and it's being used in a particular way. And that's confusing. Okay? It's not intrinsic to the lens, it's intrinsic to where, it also involves where I'm actually at. And the other thing that even makes it worse is it depends on where the object is in this case. How far away are you holding the magnifying glass from the actual thing you want to look at? So let's talk about, how do you actually describe with these issues what the angular magnification is. Well, what we're going to do is we're going to have a standard place that when we list the magnification of the lens, we're going to assume you placed your eye in a specific place, and we're going to assume you placed your object in a specific place. And we're going to say you put them in a location where you can see the fine detail most clearly. Okay? And that's where you're going to put both your eye and your object. That's going to be the guiding principle about how we should hold this, essentially. So, if I want to see a fine detail very clearly, you want to have the thing that you're looking at be as close to your eye as you can see clearly. Okay, so if I just ignore the whole lens thing for a second, if I wanted to look at a pencil and I want to see the letters written on that pencil, I would hold that pencil as close to my eye as I can until it started to become blurry. If I brought it too close to my eye, it would blur out and I couldn't see anything. So I need to not bring it, I want to bring it to exactly the distance that is as close as my face and I can see crisply. That distance is the near point. Now this is another thing that will be a little confusing for people who are younger. That distance we will use will be 25 centimeters. For you, it'll actually be something more like 7 centimeters. But they're not going to list this assuming that you're the person looking through the lens. The way they list it is they assume that the nominal person, which is to say the person who has the worst vision, who does not need it corrected, who has a near point of 25 centimeters, is the person who is looking through the lens. They want to hold it 25 centimeters from their face. That's as close as they can hold it where they can still crisply see it. And that's what they're going to work through for this problem. Okay, and all of this description about how lenses work will assume that it's this person, who's probably somewhere in middle-aged person, looking through this lens. I should say one more thing on this. If I'm using the lens to look at something, I don't see the object itself. I see the image instead. So what this means is that I want the image to be 25 centimeters from my eyeball. Okay? That's the condition we want here. We want the eyeball to be 25 centimeters from the lens, the image.